Okay, 5.3, slope-intercept form. So we're going to take the concept of slope and apply it to graphing lines, all right, writing equations and graphing lines. So the vocabulary should kind of help with some of the language around slope-intercept form. We are going to talk about the parts of it and what they mean. So slope-intercept form has a few different parts, okay? And this is for non-vertical lines. So y equals, we call it mx plus b. So this number that is being multiplied by x is called the slope. We talked about slope in the last lesson. Slope determines the steepness of a line. So the slope is always multiplied by x in our slope-intercept form. The other number, we call that a constant because it is just a number by itself being added or subtracted from the slope. This is the y-intercept. This is the y value of the point where our graph crosses the y-axis. So this 6 means our graph will cross the y-axis with a y value of 6. So the first thing, sorry, I missed just a little bit, sorry about that. This whole thing is what we call a linear equation, and this is in slope-intercept form. Okay, so the main thing to remember is we always write slope-intercept form as y equals mx plus b. So the variable term comes first, the constant always comes second. So 6 plus 4x, that is not in slope-intercept form. So a simple example to start off, the slope and y-intercept of this graph, pretty straightforward. The slope is 5. The y-intercept, since this is 5x minus 2, the y-intercept is negative 2, okay? So really just understanding the features right now. In example 2, writing an equation in slope-intercept form. To write the equation with a slope of -4/5 and a y-intercept of 7, it always starts slope-intercept form with y equals, and we write the term with the slope first. So that's this -4/5. So we write this as -4/5 x. A y-intercept of 7 means plus 7. So the main thing that gets confused here is people will say the slope of this line is -4/5 x. That's not true. The slope of this line is -4/5. That means it's a line that is decreasing left to right. So what we're going to do now is we are going to write an equation in slope-intercept form from a graph. So the two big features we need are the slope and the y-intercept. And I always think the y-intercept is the smartest thing to find first because I think it's the easiest thing to find. So when we look at this, our line crosses the y-axis right here where I put this green point. So that is the point 0, 2, making our y-intercept 2. As far as the slope goes, we can count the slope by picking 2 points, any 2 points on the line, and counting. So the change in y goes down 2. The change in x goes right 2. So our slope is 2/2, which is really just 1. So you've got to pick 2 points. I'm not going to give you 2 points here, okay? So to write this out, it's going to be y equals, slope is 1, so it's like 1x, or just x, so x plus 2. So you're picking out those features from the graph to write the equation in slope-intercept form. Next example, writing it from 2 points. Now this goes back to the last lesson we had with finding the slope. So the first thing I'm going to show you, finding the slope, then finding the y-intercept. So remember that slope, m, y2 minus y1, and then x2 minus x1. So the way I'd write this, I do negative 3 minus negative 2 over 1 minus 3. So this becomes negative 1 or negative 2, which is positive 1/2. So the thing here, we have the slope is 1/2. We don't know the y-intercept. So this part can be a little confusing, so it's important you kind of take your time and pay attention to this part. So to find the y-intercept, with our y equals mx plus b, we know m, we don't know b. We also actually know what x is and y is for a specific point. We're given 2 points. So the thing we do here is we pick one of the points. I'm just going to pick the first point, 3, negative 2. It is an xy point, so I go into my slope-intercept form. I substitute in negative 2 for y, 1/2 for m, positive 3 for x, and I don't have a value for b, but we are going to find that. So we are going to simplify and solve. So this becomes negative 2 equals 1/2 times 3 is 1.5. And then I finish by solving for b. Subtract 1.5 from both sides. So b ends up being negative 3.5. So I'll go back to green now. So after all that work, my equation, y equals 1/2 x minus 3.5. So I'd say this is the hardest part of this lesson, is writing an equation of a line from 2 points, because it's remembering to substitute your point, the y value for y, the x value for x. So this requires the most work. So if you get to the practice, the paper and pencil practice, and you decide to do that, remember it's optional, this would be a good thing to practice. Okay? Next part, graphing a linear equation, understanding slope and y-intercept. So another good practice to have is the y-intercept. We can call that our starting value. I like calling it a starting value sometimes, because it tells us which is the first point to graph. But our slope is 2. So the first thing I do when I'm graphing slope-intercept form, I graph the y-intercept. We know our line crosses the y-axis at negative 1. We know we have a slope of 2. So what that really means is the change in y is 2, the change in x is 1. So the way I graph that, the change in y is positive 2, so that means up 2. So up 2, and then the change in x is positive 1, so I go right 1. So I count for my y-intercept up 2, right 1. And I only need 2 points to draw a line, but I'm a pretty bad at drawing straight lines, so I just continue on with my points, up 2, right 1, up 2, right 1. And my slope is the same throughout the whole graph. Now going up 2 and right 1 would be the same as me going down 2 and left 1 from my y-intercept. Down 2, left 1. You never need to draw this many points, but for me, this makes things much easier to draw a straighter line. Okay, so it's knowing the y-intercept, graphing that first, then the slope off of that. And then the final example, modeling a function, means we have to define our variables, which are it's done for us, and then writing an equation. So we've already defined the variables x and y. X is ours, so I'm going to label that on my axis, my x-axis. Y is total cost, so I'm going to label that on my y-axis. All right, and then we can do a couple different things. But to write a model, we've got two numbers here. One of those values is what I call a starting value in these context problems. The other value is the rate. The rate is your slope. So for this, just to write it out, my y-intercept, my starting value, says a plumber charges a $65 fee for a repair plus $35 per hour. Write an equation to model the total cost of a repair that takes X hours. So starting value, y-intercept, is that $65. Your bill starts at $65. The slope, the rate of change for that job, is 35. You get charged for $35 for each additional hour of work. So to write our equation, it would be y equals 35x plus 65. So that means you start with a bill of $65. That bill increases by $35 for each increase in 1 hour of the job. So for our hours, we're picking what's called a reasonable domain. So a reasonable set of x values, 0, 1, 2, 3, 4. Basically any numbers that are positive or 0, that are whole numbers, okay? I think usually a plumber is going to charge you in whole hours, not charge you for a half an hour. If they work for a half an hour, they're going to charge you for the full hour. And then we find the outputs for each of those inputs, the y values for each of those x values. So in my function, I think about it, I start with 65 plus $35 for 1 hour of work. That job is $100 plus another $35. That job is now $135 for 2 hours plus another 35, up to 170 plus another 35, up to 205. So our graph of our function, it's not going to be perfect, but it's going to be as close as we can get it. We're going to have to do some estimation here. So 0, the point 065, I don't know, between 50 and 100. 100 is going to be easy to graph. 2 and 135, a little bit closer to 150. 3 and 170, pretty close to the middle of 150 and 200. And then 4 and 205, just above 200. And it's going to maybe not be perfect, but we've got a line, a linear function, okay? So that would be our graph that models the total cost. So I've kind of thrown a lot at you with 6 examples, but the idea is that we are working through examples to understand how to attack these problems from different angles. So now is a good time for you to practice your knowledge of this with the quizzes.